Well, hello everyone, and welcome back to Adrian's Digital Basement. On today's video, I want to try to fix this video card. What we're looking at here is a somewhat obscure and mostly unknown ISA video card called the STB Res 400. It's not just a normal standard CGA or even EGA card. This is sort of an in-between card between CGA and EGA that allows output of high-resolution 640 by 400 graphics over a digital TTL output. I need this card working for an upcoming video I'm working on with a different project, and I figured it might be good to do a little troubleshooting exercise on a card like this because there are no schematics or really any information whatsoever about this card besides promotional information where you can find old advertisements. So what I'm going to be doing in this video is trying to understand how this card works and trying to go backwards from there to try to figure out what the fault is. So without further ado, let's get right to it. All right, the STB Super Res 400. As I mentioned in the intro, this is a 400 line video card. So instead of being normal 640 by 200 like CGA is, essentially the same scan rate as NTSC video, this card is designed to output CGA-like display modes, but with a line doubled resolution at 640 by 400 non-interlaced. So therefore you get much sharper text. In fact, the character ROM has a font in it. Instead of being 8 by 8 like a normal CGA card, it's 8 by 16 characters, which means that the text is a lot sharper and a lot closer actually to what you get on VGA. In fact, the IBM VGA standard uses a text mode resolution of 720 by 400 pixels at 70 Hz, while this card being 640 by 400 at 60 Hz means that VGA's font size, due to having 720 pixels across, is actually 9 by 16. But it really means when you look at the text mode output of this, it looks very similar to the clarity of VGA text, which is very different than the clarity of CGA text, which is very blocky in comparison. Now you might be asking, why does a card like this even exist? What monitors exist that could do this 640 by 400 resolution? Well, it turned out in the Japanese market, the PC9801, which was released by NEC, actually supported this same resolution on their monitors for clear text. And I think the idea specifically was that NEC wanted to have higher resolution fonts available for katakana and kanji characters to fully display properly and clearly the Japanese character set. Now, I had a video about the NEC APC, which is sort of an all-in-one MS-DOS computer that's not really PC compatible, but it's still an 8086 processor. And that was essentially an all-in-one PC 9801 sold in the US market. As far as I'm aware, the internal display on that computer actually was running at this 640 by 400 resolution for that high resolution text and also high resolution graphics. Since these high resolution modes existed in monitors and computers in Japan, what started happening was that companies imported those high resolution monitors to the US and marketed them with 400 line video cards like this, with the promise specifically of much higher resolution color text over regular CGA and potentially some better graphics modes as well. Now, I think this stuff all came out before the EGA standard came out, and EGA, of course, also had a higher resolution text mode at 640 by 350. While not quite as many lines as the 400 line cards here, it used a character set of 8 by 14, which was nearly the same and offered much more improved graphics and text mode. With the release of EGA though, that meant that all of these sort of in-between cards like this pretty much fell by the wayside. And I think the only reason why this was probably being sold in 1986 was to support any of those people that still had those 400 line monitors floating around that they wanted to use on their IBM PC or PC compatibles. Looks like this one has a serial number of 16,511. Don't know how many of these cards were sold because, like I mentioned, there's really no information about these cards out there whatsoever. Now, what makes this card kind of interesting is that it uses a Motorola 6845 CRTC. This is the timing controller that handles the refreshing and the vertical and the horizontal sync outputs. And it's the same chip that's used on a CGA card and the MDA card, although it wasn't used on the EGA card or anything beyond that. And something that's interesting about this card is it offers CGA and MDA compatibility, as in monochrome and color. And it can do that in one card all at the same time. Other than the more capable later EGA and VGA cards, I'd never heard of a card like this that was sort of a dumb card, so to speak, that could support both of the standards in one card. And even though you see a couple things that look like ROMs on here, this actually doesn't have its own BIOS ROM. This truly does work just like a normal CGA card or an MDA card, where the BIOS ROM that controls the video circuitry is actually built into the motherboard in the system BIOS. Which begs the question, if the system BIOS is controlling the video card and it thinks it's a normal CGA card, well, how exactly is this supporting 400 line output while normal CGA only has 200 lines of display? Well, we'll get to that question in a little bit, but there's some interesting trickery that seems to be going on this card to facilitate that. So the first thing I want to do is take a look at the ad that talks about this card. This is an STB advertisement from a magazine. I found it on Google Books. And beyond this advertisement, I couldn't really find any other official information about this card whatsoever, except for maybe the odd advertisement of places selling it, but otherwise no reviews or any more detailed technical information about the card. So on this top image of the advertisement from STB, it shows off the collection, which are their 5 video cards they were selling, I guess, at this time. And in the middle is the STB Super Res 400. That's the card we're dealing with here. This has sort of a brown PCB, while mine has a green one, but otherwise this looks exactly the same. Moving down on the ad, it talks about all these different cards that they actually sold. The one on the left, I guess, was the Chauffeur. It seems to be the video card you were waiting for. I don't think you knew that, did you? But yep, it is. It automatically displays color graphics software on monochrome monitors without inconvenient drivers or pre-boot software. That's actually pretty cool, because if you bought an original IBM PC with a monochrome monitor, there was no graphics modes at all, other than text mode graphics, so to speak. Later, you could buy Hercules cards, which did offer a pixel bitmap black and white style graphics image, but unfortunately it was not compatible with CGA software. Now, there were software drivers you could run that would translate on the fly CGA graphics into something that was compatible with your Hercules card, but unfortunately it resulted in games that were kind of, well, they had the wrong aspect ratio, and that's because Hercules has 350 lines, unlike CGA with 200, so there's no way to really scale the image properly. But worse than that, it actually offered pretty bad performance as well, because you had this software layer that was running doing this translation. Now, one interesting fact is I have a much later monochrome / CGA card, and it's one that's really small. It's basically almost the size of just the minimum size of an 8-bit ISA card, and it can do monochrome and color, and it has a mode like this Chauffeur card that allows you to use a monochrome monitor to display CGA graphics on it. And even more wild on that card is it displays it with shades of gray on a regular monochrome monitor. And I'm not talking about just 2 different shades for like white and then intense white. It actually does multiple shades on a monochrome monitor. I really need to break that card out. It's installed in my IBM PC 5150, and we need to take a look at the signal on an oscilloscope to see exactly how it's doing that, because I've honestly never seen any other card that can do that. Take a standard digital TTL monochrome monitor and display shades of gray on it. Anyhow, perhaps it was this Chauffeur card here that started the whole trend of allowing that, and it even says that it can do it in shades of gray as well. So that Taiwanese card I have probably was just copying whatever technique STB figured out for their Chauffeur card, which is frankly pretty cool. If anyone knows more about this Chauffeur card, definitely put a comment down below, but personally I've never run across one. The next card is the Graphics Plus 2, which seems to support both MDA monitors and CGA monitors, and it has an additional 16-color graphics mode. I think the Graphics Plus 2 card has 32 kilobytes of RAM on it, so it offers 320 by 200 resolution at 16 colors. Very similar to what EGA was able to do in that same resolution, and of course, very similar to the Plantronics display format as well. But from my understanding, there's no compatibility between any of these STB special modes and the Plantronics modes or any other special mode like Tandy, which could also display 16 colors in 320 by 200. And next we have the middle card, which was the Super Res 400. That's the card we're going to be working on today. This card can display clear monochrome quality text, but on color screens, and enjoy superior graphics. High resolution display of Lotus 123 Symphony's made easy with software support. The Super Res 400 designed to be used with high resolution color monitors, specifically monitors that support the 640 by 400 standard. And then the next card over in their lineup was the Color 16 XVI, a less expensive IBM compatible color board for your standard RGB and composite black and white monitors. So that would be just like the CGA card, at least from a video output standpoint. It seems to include a parallel port, but doesn't really seem to add any other functionality. I guess it just costs less than the IBM CGA card, which maybe was pretty expensive at the time. And the final card was their Mono Plus, and it says no other card can match the crisp, clear, easy to read monochrome text. That doesn't make sense because it's digital TTL signal. It's the same crispness and clearness of any other monochrome card. So you got me on exactly what is special about that card. Now, there's probably people screaming at the screen right now telling me that this STB card was also sold and marketed by Tandy Radio Shack for use with some of their monitors, which did support this high resolution graphics mode. I'm actually fully aware of that, and here's the manual for that card, which really is the only piece of documentation we can find that has anything to do with this STB card whatsoever. And it was marketed by them as the Deluxe Graphics Display Adapter, catalog number 25-3047. Now, it's really cool that this manual has been archived, and it does contain some decent technical information about this card. No schematics, unfortunately, but at least it has programming information and some information about the dip switches that are on here. So right off the bat, it says here that this was designed for use with the Tandy CM1 color monitor. That's not really the case. The STB card was not designed with that monitor in mind because there were other 400 line monitors out there, not to mention multi-frequency monitors you could plug into this and have them work as well. But definitely Tandy's CM1 monitor, which you may have heard of recently in V Westlife's video, was a monitor that was absolutely compatible with this card, and it allowed you to keep using it beyond its original use case, which was with the Tandy 2000. It mentions here that this card is compatible with the Super Res 400. I mean, yeah, of course it's compatible. It is the same card, but it's also compatible with the Graphics Plus 2. So we know that that Graphics Plus 2, which we saw in that advertisement, which mentioned a 320x200 mode by 16 colors, is programmed the same way as this card. So if any software out there exists for the Graphics Plus 2, then it should absolutely work on this. So if you're aware of any software for that card that displays 16 colors, definitely let me know down below in the comment section, because I would like to be able to test this out a little bit better. So some of the features of this card we've already talked about a little bit. 8x16 character cell, has dual character sets in ROM, the standard CGA modes, 320x200 4 colors, 640x200 at 2 colors, so basically black and white for all intents and purposes. But then we have the special modes, 320x200 at 16 colors, 640x200 at 4 colors, and 640x400 at 2 colors. Now see here this asterisk. Each of the 200 line modes is line doubled to make it work with the 400 line monitors. That's actually a really key point. That tells us that the monitors that were designed to plug into this were not multi-frequency like EGA monitors were. So for you to display these legacy graphics mode, the card itself had to line double the output so that it would display in 400 line modes. This is exactly how VGA displays 320x200. It's actually line doubled and really displaying at 320x400. It's just you don't have access to those extra pixels. Continuing on in the manual, it talks about how the dip switches work, which is quite helpful. There is a mode switch that allows it to respond as only a CGA card if you set switch 1 to on, or if you set it to off, it's monochrome or CGA in one card. As I mentioned, that's a feature I've never really run into before. If anyone knows of any other like 8-bit ISA type cards like this that can respond to both, I'd be really curious to hear about that. Now further on in the manual, it's just talking about the CRT-C. It says 6845, but the chip that's on here is a 6545, which is generally compatible to 6845. They're kind of interchangeable. I think Moss came up with the 6545, and it's in use in the pets and stuff like that. But I think in the case of this card, you could probably substitute either chip on here and either would work. Next up, there's a little section here on how the text mode memory works, and basically you have even and odd bytes. One is the actual character, and the next is the attribute. And again, this is identical to the way CGA works, and therefore EGA and VGA work the same way as well because they're really backwards compatible with the text mode of CGA. And then on this page, it talks about the graphics mode register, where you can set up these different graphics modes. But one thing that's kind of interesting is we can see all the additional graphics modes that this thing supports, but we have one here that wasn't mentioned up at the top, and it's 320x400 at 16 colors. And there's even 640x400 by 4 colors, which also needs 64K of RAM. That's a relatively high resolution mode that would be really cool in something like DeskMate. I don't know why these modes aren't mentioned higher up when it listed the capable modes that this card has. And as far as I'm aware, nothing ever really used these higher res graphics modes, which, especially the 320x400, that could have allowed for some pretty cool dithering using, mixed pixels and mixed colors to give more than the apparent 16 colors on this card. This is the list of the register values for all of the various graphics modes, and this is just typical. But it's very nice that they provide this. That means that if you were trying to write some software to utilize, say, 320x200 at 16 colors, you could just set up the CRT-C using these particular values and you'd be off and running. Now what's funny though is I compared this table to what CGA cards are using for the normal CGA modes. And if you can believe it, it's exactly the same. And what's really interesting about that is the CRTC itself is what's outputting the horizontal and vertical sync signal to go to your monitor. And as far as the BIOS knows, this is a standard CGA card. When it goes to set it up, it sets it up to output a normal 15 kilohertz horizontal and 60 hertz scan rate. But what you get out of this is not that. You get the 26 kilohertz scan rate at 60 hertz with that high resolution line doubled mode. So that means that there's obviously a bit of trickery happening on this card that takes those calls to program the CRTC and does some translation. And that's exactly what I think is happening with this ROM chip right here. This is not a normal BIOS ROM like an EGA or VGA card has. This thing just uses the standard CGA mode on the BIOS. But I think what happens is as the writes come in to go to the CRTC, they are translated by this from the standard CGA or MDA values into values that are going to end up giving the correct scan rate out of the video output here. And when we look at the dip switch settings on this card, which is higher up in the manual, notice it has 4 settings here, which just seem to, well, all be the same. It says 25 kilohertz high frequency monitor. I think what they had in mind here is that you could have different translation tables for different monitors. So you could have customized values designed for specific monitors that would properly output the exact horizontal and vertical sync rates that are necessary to work with that particular monitor. Now, I haven't even talked about the fault with this card yet, but it doesn't involve this EPROM or the output or the CRTC. That part of the card is working just fine. The fault lies somewhere else, and we'll get to that in just a second. I just wanted to go back to the manual here just to show that there is a little bit more technical info, like it does have the pinout for the DE9 connector, and it's mostly the standard pinout for a CGA monitor. So you could plug a CGA monitor into here, and the signaling would be correct. It just, obviously the scan rate would be wrong. And then going down a little further, we actually have a little bit of information talking about the jumper blocks and the switches that are on here. Now, there is some information that is incorrect. As far as I'm aware, all of this stuff is fine with the switch summary, which we've already looked at. But what is wrong is item 4 here. Jumper W1 is not connected. That's this one up in the corner right here. It is absolutely connected. And on this board, if you're going to operate this in normal mode, you need to have no jumper installed on W1. And then for W7, which is right here, it's 4 pins with 2 up, 2 down. It says that it should have a shorted plug on the lower 2 pins. And indeed, that's the case. That is correct. And if you put the jumper on the top 2 pins, what that does is it seems to force the character generator into an 8x8 character cell. So that changes your font from the full 16 lines, which looks correct on the 400 line monitor, to really a squished font that only has 8 lines, which is more like it's designed for use on 200 line displays, like the old CGA, that is. So that's the overview of the STB Res 400. An interesting video card from a time where people were trying to get these 400 line monitors working on their PCs, and you needed a specialized card like this to make it possible. Now, you might be asking, why do I even have this card? Well, the reason why is for that future video, I'm trying to get it working with a 400 line monitor. And I went through every single video card that I have, and not one of them supported 400 line mode, or at least I didn't have any that were documented in a way that I could set them into 400 line mode. I did find that there are some, and I mean some very few EGA cards and very specific versions of them that do seem to support the 400 line mode. And what's nice about those, of course, is they are EGA cards, meaning that they're compatible with the EGA 320x200 graphics mode at 16 colors. They obviously line double it to 400 lines, just like this card does. But unlike this card, where that graphics mode is not supported by pretty much anything, there's tons of software and tons of games out there that supports the EGA modes. So that's obviously the way to go if you're trying to use one of these 400 line monitors with an old PC. But like I mentioned, I don't have any of those cards, and I'm not really sure which cards have that mode and which don't. And unfortunately, of the 20 or so EGA cards that I have, I went through and tested every single one of them, and I'm 99% sure that not one of those cards supports the 400 line mode. So I had to get this card, which unfortunately has a fault. Let's finally talk about what that fault is. So what I need to do is get this thing plugged into a motherboard and fired up so I can show you what the fault is. Now, that brings me to the first problem. Obviously, if I plug this into a motherboard like this, well, you can't really see the card from the top-down camera view, and I'm going to need to be probing around on here. We're going to have to try to do some troubleshooting while the card is operating, and that's not ideal, just because of the way the camera is set up here on the bench. So I've come up with this little test setup here to help facilitate this particular diagnostic process. It's a normal 36SX motherboard, the one you've seen on my channel many times. I have an IDE card in here with my compact flash card, XT IDE card for the BIOS, and then I'm just using a normal ISA riser card here so I can plug any ISA card into this and keep it parallel to the motherboard So we can run this and do some testing on it while it's powered up and in use. Of course, this thing is sort of floppy right here because nothing's holding it up. So I'm just going to use this audio cassette here. It's like the Lion King or something like that. We can just stick that right there. And that way I can push down on this and we don't have any issues. So as I always mention, it's always really good to make sure that your test setup is working correctly. So to facilitate that, we're just gonna get this all plugged in using this normal CGA card here. And this is my favorite CGA/MDA card from VTech. For video display, we're gonna be using the RGB to HDMI. So we'll just connect that up. Got my little keyboard here and let's power this up. Okay, something is very wrong. The computer sounds weird. That's exactly why I said it's good to test first, right? Because we need to make sure we are fully operational here. Okay, we have RGB to HDMI. We saw a flash when I first turned this on. Let's try this postcard here, see if we're getting normal postcodes. So that's able to read the bus without any issue. You know what? I'm having a thought here. That I recall this motherboard has issues sometimes if I use these slots over here specifically. So what I'm gonna do is I'm gonna move this over one, and I'm gonna move this stuff closer. I couldn't tell you why, but there seems to be some kind of issue where these slots on the far edge here just seem to result in some stability problems with this particular motherboard. Okay, sounds normal. And we have a system that appears to be booting. So I'm really glad I did that because I didn't want to go to test this STB card and have it not work because of the other issues going on with this whole thing. Let's turn this off and jiggle the cards around a little bit, and we'll just move this stuff back and forth. Let's see if that made any difference. Okay, it's working. Like I said, I'm quite sure it has to do with this motherboard and these slots over here, and it's nothing to do with the riser. It's some electrical issue. And I've just noticed that anytime I put stuff all the way over here, it seems to cause instability on this particular motherboard. Good, we're booting, and that means I should be able to turn this thing off. You'll notice that I have a little pink power LED there just to help me remember don't unplug and plug cards in while the thing is turned on. So we'll take out that CGA card and we'll stick in this STB card here. Just move that for a second just to help me get this big, long, heavy card in. And then we'll stick the Lion King tape under here on this part of the card there. So it's a little floppy over on that end, but should be okay. And we're gonna be using the RGB to HDMI. And that's why I really love this thing, is if you do have a card that has a weird video output, then you're gonna be able to get it to display correctly using the RGB to HDMI. In preparation for this video, I went ahead and I made the profiles for this card already. So I'll be sending these over to the team. That way, if you have one of these cards, then you can use it with an RGB to HDMI. So I have a few different profiles here. So there's 26 kilohertz at 40 columns, and there's one for 80 columns. Unfortunately, there's a slight difference in the way the video is output between those two, which causes it to shift over slightly. And that might be something we could fix in this translation ROM if we could ever figure out how that all works. Then there's also 26 kilohertz graphics mode, and then there's a monochrome text mode as well that also has slightly different timing. They all sort of are compatible with each other, but as I mentioned, what happens is if you're in 80 columns mode and you switch to 40 column mode, the text is just like shifted over slightly and kind of some of the letters are cut off. But we'll be able to use this 80 column mode right here for just booting up this system. And here we go, 3, 2, 1. Hopefully this card is working. I haven't used it in a while. Ah, there we go. Yeah, we're good. All right, so we have a fault here where you can kind of tell with this screen what's going on. The tick mark there in the Chicket logo should be red, and the red seems to be missing. Now you might jump to conclusion and think that the problem is that the red output from the 9-pin connector is not working. But let's gather some more evidence here on like what's going on with the fault, because you'll see very quickly that is not the case. So let's run through all the video tests. So first off, did a RAM test of just 16K because it thinks it's a CGA card and that's all CGA has. That passed fine. So we have various text pages, those are all good. And then we have various text modes. We have 40 columns, 80 columns. All this stuff is gonna work just fine. Now, one thing you might notice on this screen is there is a light gray color there. And a light gray color is formed when you combine R, G, and B together. And we see it there. So we know that it's not actually the output from the red signal on the pin here. And there's another confirmation. This text mode here is showing us all the possible text mode colors, and with the background colors, they're working fine. In normal CGA text mode, you can only display the first 8 colors for the background color, which is black through that white color. And you can see all 8 of them right there, and they're all working. So the red output from the card right there is 100% confirmed working perfectly. But then if you notice the horizontal lines, which are all 16 colors, any of those colors that have a constituent red component to them, like red, magenta, yellow, and white, it's just missing the red information altogether. So this is great, because we don't have schematics for this. We're going to need to try to figure out how this card works, and we really need to start to narrow down where this fault might lie. So all the parts of the card that make their way to the output, the connector that goes to your monitor, that circuitry there that drives the monitor, that could easily have a failed buffer or something, but that's not the fault, because we know the red is there, but somewhere in front of that is the issue. Now back to the diagnostics here. Here's a graphics mode, and this should just be entirely white. But notice, we're getting missing pixels, so to speak, right? You see the solid white line over and above and below the text? That shouldn't have those purple pixels in there. It should just be all white. Now this is a great clue as well. On a CGA card, which this for all intents and purposes is, it has 2 separate paths for getting the memory displayed to the monitor. One is the text mode, where there's information about the character itself that's being displayed, and then there's also information about the color or the attributes that should be applied to each character. That's the even and odd byte that we saw briefly in the manual. And then the graphics mode is a different path, where it takes the contents of memory and displays it in basically pixels. It uses shift registers to shift it out, and it displays it in lines. And the way color is displayed on a CGA card is it uses something called bit planes, where you have 2 different bit planes overlaid on top of each other. And these bit planes are a bitmap representation of all the screen information, like all the pixels on the screen. But remember how CGA low-res graphics mode has 4 colors available to it. That means that there are 2 bit planes. And when you combine those 2 bit planes and you set the bits appropriately, you get those 4 colors. So if the bits are 0 and 0 on the 2 bit planes are overlaid on top of each other, you get black. And if they are 1 and 1, you get white. Well, what happened on that screen when we were just looking at, we had columns where instead of getting 2 bits for white, which is what the whole screen should have been, we were missing columns of bits that were resulting in a value that was 1 and 0. And in that combination, in that palette that's being used, you get that magenta color. And we can be pretty sure if we go through the rest of these here and it gets to the one that has the full color screens, we're going to see that same issue with the yellow and the red palette, where you're going to have lines where I guess we're going to see stripes of red. Okay, this is 640 by 200. This is the high res mode that doesn't use any bit planes because there's no colors available, it's just one color. And we are getting the exact same stripes in this. It's just that instead of it being white, it now becomes black because that pixel is just missing altogether. Now, here's what I was talking about. So there it is. So that brown color became red, and the blue is just missing, and the green is missing. You know, you can kind of see that the pixel in the bit plane is missing altogether, and then that just results in the underlying color showing through on the other bit plane. But you can see that in the purple box, there's no issue whatsoever. That means that all the pixels in the memory on that bit plane are working fine. And when you take a look at the card, these are the RAM chips, and these are 4416s. That means 2 of these chips make up 16Ks. Each one is 4 bits wide. And 2 of these is the original amount of memory that the CGA card has, and then these other ones are needed for the higher resolution or higher color graphics modes that this card does support. Now the thing is, when we ran check it checked the memory, and it said that it was fine. I happen to know that the way check it checks the memory on a CGA card is it just fills the 16K with a bunch of data and then just reads it back. And I think it alternates the bits a little bit or whatever, something very simple. But it essentially is reading and writing directly from the RAM on the board, because the RAM on the board is not only available for display out to the monitor, but it's available for the CPU to read and write from at any time as well. And check it is telling us that the memory itself is totally fine. The CPU is able to read and write the memory without any issue whatsoever. But because this has 64K, we know these extra chips are used for the higher res modes, and check it's only going to really look at 2 of these chips. But you really have to imagine that all the text modes and the CGA graphics mode and the RAM check and check it, all of that activity is happening out of the same 2 chips. And there's a few ways we could go about trying to figure that out. Well, one is these are in sockets. We could just take out all the chips and then start putting chips back on the board until we start getting a functional CGA mode. And then we'll know that those are the two chips that are relevant, and the rest here aren't being used, except for the higher res modes. I think the first thing I want to do is start taking these chips out and seeing when we start having broken video on this machine. Okay, here are the chips over here. They're taken out exactly the same way that those were in there. Let's see if this card works with just these two chips installed. All right, here we go. No. So what I'm going to do is I'm going to install these bottom chips here. I want to see if this brings the card back. And maybe these are the ones that are actually in use on this card for regular CGA mode. Let's just turn this on and see if it beeps. Ah, it's still beeping. It could be that the RAM layout is not what I expect. And it's not just linear, but maybe it's like interleaved inside the memory in some special way. What I'm going to do is I'm going to install all 4 of the chips on one side. And let's see if we start to get some amount of text. It's going to be all messed up because we're going to be missing 4 bits. We're only getting 4 bits of the memory. Okay. It looks okay, which is weird. It looks totally fine. What I'm going to do is I'm just going to take out these 4 chips on this side. Now see if we have a functional card with 32K of RAM. We do indeed. Let's test the video RAM and check it here. Okay, that passed. All right, so CGA is essentially working perfectly right now. We still have our same exact fault here. So what I'm going to do now is I'm going to take out 2 of these chips in pairs, and I want to see if the card can operate with really just 16K. Okay, so it doesn't operate with those 2 chips. And let's try it with these 2 chips. That didn't work. So how about with these 2 chips? I mean, I'm just sort of trying all the various combinations. No, that didn't work either. So the reason why I'm doing this is I really want to just try to eliminate the parts of the board that aren't necessary for operation for us to do this further troubleshooting. So it seems to require the 32K on this side for it to work properly. There it is. Now what we can do is we can pop these chips out here, and I'll just swap in the other set. And this will rule out that we don't have an issue with those particular DRAM chips. I had a dot on these ones here, so I knew that those were the ones that were on this side originally. Let's see what happens now with them swapped around. Okay, same problem. And if we test the video RAM, that tests perfectly. And of course the graphics modes, they're going to be messed up in exactly the same way. All right, so we've ruled out that the RAM chips themselves are the problem. I'm very confident in saying that it's not a problem with the sockets themselves either, because if it were, the check it CGA RAM test would fail. And that's because, as I mentioned, that works by filling up the entire 16K buffer with data, reading it back by the CPU, and it does that a few times. So if there was a problem with one of the data lines with a trace or one of the sockets, that would absolutely fail. And we know it's not the display output, at least the final stage, that generates the video signal. There's some buffer chips there that generate the video signals, and clearly that's not the problem. The problem we're having with this card is somewhere between the RAM itself and whatever is generating the video display, which if you think about the 640 by 200 mode, that is literally just outputting a serial stream of data from the RAM to the display. And the fault is exhibited there among the other modes as well, where the bit planes are showing it. But that is really an obvious place with that black and white 640 by 200 mode, where we just have missing pixels. Now the manual for the card actually has some really useful information that can help us with this. So look at what it says about the 2-color mode. That's 640 by 200 in 2-color mode. The CGA card looks like it's accessing the RAM in 16-bit chunks, which is confirmed by the fact we have to have 4 of those chips installed on the board, and we know each chip is 4 bits wide, and that implies 16 bits. And when you see even and odd byte here, you actually see that there are 16 bits that are relevant to make up the video signal. Now it's saying C0 as in color 0, which happens to be white in the most of the normal modes. So whenever one of these bits is set to 1, then you're going to get a white pixel on the screen, or whatever color is described by some other register somewhere else. But what we're seeing is that we're getting those columns of missing pixels. So we're missing one of these bytes, where instead of it being set to 1 when it's that way in memory, it's actually coming back as a 0. If we look at the 4-color mode, which is the standard CGA color palettes, and you can see them described here, cyan, magenta, white, black, for instance, it's similar, but instead of each bit all being for 1 color, it's actually 2 pixels that describe the color of 1 pixel. And C1 and C0, see here, C1 and C0, and remember, where it's looking like it should be white, which is 1 and 1, we're getting magenta, which is telling us that it's the C0 pixel that should be a 1, but it's actually coming back as a 0. And the C0 pixels are those ones, those ones, those ones, and those ones. So 0, 2, 4, and 6. So we're kind of narrowing it down here. And on this page, it's now talking about the text mode. The even byte is handling which character is actually displayed out of the 256 that are available. Those seem fine. We're not seeing any issues there. But it's this odd byte that is describing the foreground background color, which we're seeing the issue. And we know that the background color appears to be, well, working just fine. And I think the extra bit here, the intensity bit, is used for flashing or underline or something like that. And that's working fine as well. We saw that in the check it text mode. So those bits are okay, but it's the foreground color that's not working. And it's the red bit that seems to be the problem. And that is the odd byte bit too, because that's where the red is missing entirely, and we're always getting a 0 there, which just means that whole red component is missing from that particular character. Okay, so we know the issue lies right here, but we know it's not the RAM, it's not the socket, and we know it's not the output of the display buffers. So it's something in between the RAM, obviously, and this that is causing our issue. But one thing we know for sure is this problem is affecting both text, and specifically the attributes, and the graphics mode. So it's both of those modes that are affected. And the thing is, I'm pretty positive that the circuitry that generates the pixel-based graphics on a CGA card is separate than the text and the attribute color stuff. And it gets mixed together at the end and selected depending on which mode you're displaying. So the problem exists between the RAM and the graphics circuitry that generates both of these modes. So in other words, I think the problem is very close to the memory itself. Now, it turns out that someone has taken the IBM CGA card schematics that IBM published and recreated them in KiCad. So we have something a little bit easier to read. The original schematics are kind of in the back of the technical manual and a little bit of a pain to look at. So we're going to download these and we're going to take a look at the CGA card to see if we can kind of decipher the way it works, which I am sure is relatively similar to the way this card works. All right, so here on the CGA card, we have the 6845, that's the CRTC. Really, this is handling all the memory address lines. That's the MA lines here. And if we follow these, they go through some latch chips, and then they're going to make their way over to the actual memory that's on the CGA card. It happens to be these 2118 chips on the original IBM CGA card. So the CGA card itself looks like it has 8 RAM chips. So even though it's working in a 16-bit fashion, I think, with the odd and even bytes as well, it's doing that with just 8 chips. It seems that this card, because this is requiring all of these 4 chips to be installed, is actually working in a 16-bit fashion. So it's obviously a little bit different than this card. But yeah, these MD lines or memory data bus lines, these are going to make their way somewhere in the schematics here to the rest of the display circuitry. So let's find that. So on this page, we have those data bus lines that come from the RAM chips, and they go through these sets of buffer chips here. There's a latch and a 244. And when you see a combination of a 374 latch and a 244, and that sort of facilitates turning one set of RAM chips into that even and odd byte. And when we look at the output of these chips here, that makes its way, well, it goes into this chip here, which has to do with some overscan stuff, probably like border color, I'm assuming, but then it goes to D0 through D7. What D0 to D7 is on the CGA schematics is the ISA bus connector itself. So it looks like this is what's connecting the RAM to the ISA bus. So that's for the CPU to read or write from the RAM itself. So that's the path on the STB card we know is working, because the CPU has no trouble reading and writing from the card. So for whatever chips on this card handle this part of it, they're fine. And then we look down here, there's some more chips here. These 273s go to the CC and AT. I bet AT is attribute and CC is character. This is probably the text mode here. And yep, you can tell it is, because look at this. The CC stuff goes specifically to the character generator on the CGA card, which is a ROM chip. Those are the 256 characters that get generated. And then the AT bits are the attribute bits that make their way somewhere else. Let's find those in a second. But these are what make their way over to determine what text color is in use. Pretty sure that 273s are latches as well, and it's for the same reason. It's the odd and even byte, it's getting split, and then one of them needs to go to this character ROM chip. So as that particular memory location is being read by the CRTC, the character generator, which based on these lines here that come from the CRTC, is generating the specific row of pixels for the character being generated, and those are going to come out of this and go into a shift register, which is this LS166, and that gets turned into actual pixels that get written to the screen. We know from our notes here that whatever's happening on this card to do that is working as well. So let's find out where these AT signals are going here. Okay, so over here we see AT lines, but we also see the CC lines again. And notice these are 166s again. These are shift registers. These are converting these pixels into a display output. These are going to be used for the graphics modes. Without a doubt, these are used for the graphics modes. And I think if you're running in one of the color modes, it probably, one of these is used for one of the bit planes and the other one's used for the other bit plane. So I think what's happening is when you're in the low res mode, this is bit plane 0, C0, and there's bit plane 1, C1. And then when you're in the 640 by 200 mode, all we're going to be using is C0. But when we go back to the manual here, we can see there's the C0. So that would be like the equivalent of the shift register that's converting those pixels into actual display. And this is the bit that's bad, right? And that matches with the monochrome mode. It's all C0. But here's the issue. I don't think the problem's happening up on here, C0 or bit 2. It's only happening on this odd byte. It's happening every 16 pixels when you're displaying the high res mode. And of course, in the low res mode, it's going to be happening every 8 pixels. Because remember, these two bits are combined to create 1 pixel, right? One of these color pixels. Now, when we take a look over here, we know it's data bit 2 that the problem is happening with, which is MD2, and that translates to AT2. AT2 is part of this chip right here, and that makes its way to D0, which makes its way to red. So I'm not surprised that there are a lot of similarities between this card, the STB card, and the IBM CGA card. And that right there tells us that if we were dealing with this exact problem on a real IBM CGA card with this AT2 line missing and also this AT2 line up here that would create that missing pixel on the C0 here, then we know for sure that it would be this particular IC right here that's the problem. This pin 15 will be stuck at 0 all the time. And that's hooked up to data line 2 on the RAM chips. Well, one of the problems is with this card is that I don't see any 74 LS 273s. I wrote it on my little piece of cardboard there. We have lots of 347s, 347, 347, 347, and we have these 299s here and here and here. And then on this part of the card here, we have these GAL chips, and this one says clock mem, I don't know, clock mux, and clock ran, and so these have something to do with obviously, well, reducing the complexity of this card and probably doing the line doubling and other things that are happening on this card. So I'm thinking that the issue has got to be probably with one of these chips here, or I guess potentially one of these chips, but I'm kind of feeling like it might be these right here. Now, one of the things that we're unable to test on this card is we can't test the additional RAM on here. We don't have any access to those higher graphics modes. We might be seeing that same problem on these bits over here, which are probably connected to the same 374s, which I think are all just latches. So I have a feeling what they did here is instead of using these LS273s for the character and the attribute buffers, so to speak, they're using these chips here. So I think that's where we need to start taking a look. We need to kind of see where the data lines of these connect to these chips. And then what we can do is look at the inputs and outputs of these latches and look for that stuck bit. Okay, so right off the bat, I'm sorry those weren't latches, the 374s, these are flip-flops. So what's really important with these flip-flops is we want to make sure that the outputs here are changing high to low. Like we see normal looking activity on the outputs of every single one of these flip-flops. And that's the Q pin specifically that we're looking for. And here's the pinout for the DRAM, and it's pin 2, 3, 17, and 15 that is relevant. And remember, we are seeing that it's bit 2 specifically that's not working. And we can pretty much assume that's going to be pin 15 here. So let's take a look at pin 15 on the DRAM, and let's see where it goes on those flip-flops. Multimeter's ready. Let's just go over these chips here. See if any of these are connected to that pin. So far, nothing. Okay, so we have a connection over here. It's 373, which I'm pretty sure is also a flip-flop. There's another connection right there. Same pin. No, different pin. So that's another 373. So it could well be these chips over here. So there's 4 of them there. So let's try pin 15 on the next chip here and see if it's over here. Yep, there it is on that one. There it is on that one as well. Okay, so I have a feeling with these flip-flops, we might be dealing with one set of these that talks to the 8-bit ISA bus, and the other one is going to be handling the attributes and the character. That's my guess, at least. So we're on pin 16 on this chip. I just looked up on the data sheet. That's an output. So that's going to the DRAM as an output. So this is loading data into here. It's not for reading. So that's obviously not going to be our issue. Okay, but on this chip over here, the pin we're on is 17, and that's an input. I just have the data sheet up on the screen. I know you can't see it. So this one here is used as an input. So I'm going to put a dot over here because that is a suspect. Okay, so now I'm on that chip there. Let's see if we can figure out where over here it's hooked up. Okay, it's that pin right there, which is also an input. So that's good. So we know that that's suspicious. And I'm assuming it's going to be on this chip on an output pin, and it is. That's 5Q. Then this RAM chip here is connected to this other flip-flop there. So data line 3 on these chips, that's bit 2, is making their way to the inputs of these two chips. These chips right here might be going to those chips. So what we can do is just pop one of these in here, and I'm just kind of curious now. So let's look at that one there, and let's see if these make their way to these chips. There we go. It's right there. Yeah, same exact pin. I'm pretty sure that... Oh. Oh, look. It goes there too. So my little running the multimeter over here, I didn't do a good enough job. So these are actually parallels. Okay. So that pin there that I was just on is an input. So this chip is a suspect as well. And that means that this pin here is making its way there. That is pin 7, which is also an input. Okay, so that is the same suspect for these two chips. And how about this one? Where does he go? Does it go here too? Nope. Here we go, it's over here. And we are on pin 7, which is 3D. So that's also an input. And that means that this is probably also one of the... Yep, there it is. And that is pin 17, which is an input. Okay, so there we go. We found our two suspects here. It's one of these two chips. It's either that one, or these two. All right, so that's excellent. So we don't need to go removing those from the board and just swapping them all out. What we need to do is hook up the oscilloscope and just start looking at the inputs and the outputs of each of those chips. I went from bit 2 on each one of the DRAM chips to the flip-flops. We don't know for sure if that's the way this thing is designed, but all I really need to do with the oscilloscope is just grab the probe here. We'll get this fired up, and we'll just need to look at all the units on these flip-flops at the ins and outs, and we should be seeing activity on both the ins and outs on all of these, especially when we're displaying all that color text or the graphics mode. All right, so this is the test pattern I'm going to use. It's this high-res graphics mode where we have the missing pixels. And I'm just hoping that this one is going to exercise all the various flip-flop units there so we can figure out which one of them is stuck, always outputting 0. All right, so let's just start on this random chip here. Let's make sure we're getting 5 volts. Yep, there it is, 5.1 volts. And now I'm just going to go through all the various signals on here, and we're just going to look for problems. So that's 1Q, so that's an output, looks fine. Input, looks fine. Certainly a lot of noise there, don't know what that's all about. Doesn't seem to affect the operation, I guess. We just need to make sure that the inputs and the outputs look the same. So we're on 2D, that's an input, there's an output, fine. Input, that's an output, that's an input. That's an input, that's an output, that's just ground. That is a clock signal. That is an output 5Q. That is an input, input, output, output, input, input, output. I assume looks fine. There's just not a whole lot of activity on this one, but yep, guess that's okay. And then we're at 5 volts. Okay, so that chip, everything looks fine. What I would expect to see is that when we had a problem, we wouldn't be seeing an output on one of those particular units. So that one there looks totally fine. Let's look at this one. And I'm using these clips because it's easier for me to probe all the pins with the clip here. So we have an output, input, input, output, output. We have an output, input, input, output, clock signal. That's an output, input, input, output, output, input, input, and output. And that's ground. So, or that's 5 volts. So that chip is fine as well. Worrisome because maybe the problem lies beyond. But you know what? That's fine. We just need to identify that these are all working properly. And then what we can do is if all of these are good, we know the problem must lie beyond these chips. So we'll just keep going from there. Now we're on this chip here, and I I don't see anything even happening over. I'm just checking to make sure that we still have video output. I didn't want to have like crashed it by plugging that little clip in. So this flip-flop over here, it doesn't have a clock signal. So I don't think this one is actually doing anything. So we're gonna have inputs, there's an input, but there was no output. Probably like a reset pulse or something like that. So I don't think these ones have anything to do with our problem over here because they're just not doing anything right now. And it could well be that these are used specifically for reading and writing from the ISA bus. And this other one right next to it, same thing. It doesn't have a clock signal, so there's no way this chip is gonna be doing anything on its output side. So I think that pretty much confirms that these flip-flops are the ones over here that are relevant. And I just wanna double check to make sure we don't have clock signals over here on these other flip-flops, the ones that I didn't put a red mark on. So yeah, none of those have clock signals, so they are not doing anything right now. These ones do, the ones that I didn't draw a red mark on. So what I'm just gonna quickly do is I'm gonna double check the inputs and outputs on these other ones, just in case I somehow had that wrong. And I wanna make sure that each one of these has the correct signal visible on the ins and the outs. All right, well, something suspicious on this one here. So this pin that I'm on right here, which happens to be pin 15, 6Q, is stuck down at ground. And then this pin next to it, which is the input, definitely has stuff going on it, although not a whole ton of it, but that doesn't have anything happening on it. 6Q. Let's check this other one here. So this is the same pin, but on this other chip. And its input and output look identical. But on this one, that's the input, and that's the output. There's nothing. Let's see what the other pins on this look like. So there's that one, that one. These all look the same on both. Every input output is matched. Yeah, okay. Well, it's not exactly the right chip that I thought was the problem, but right there, that's the one. I think it's that pin. It's gotta be. Every other flip-flop on this board, the input and output, you see activity on both. So it's my assumption that either this chip is bad or whatever it's going to on the board is bad. And it quite possibly could be that. It might be that whatever chip it's going into has that particular pin shorted to ground. And this is where schematics would be very helpful to figure out where that pin is going exactly. So I'm just gonna do a quick jump cut where I'm gonna spend a moment to try to figure out where that trace is going on the board to see what the next chip down the line is, because that could be the fault as well. As far as I can tell, the output of the flip-flop that's not working, which is this pin here with a white mark, makes its way to this chip here, which is a multiplexer, an 74F151. There we go, we have a dead short between these two chips, 0.12 ohms. Now I wanted to check to see if, say it's shorted to ground, 4.3 megohm. That's from the output pin here to ground. Now, I just was thinking that if it was shorted internally or something and to 5 volts, same. Let's check one of the other pins. Same. So this is one of the working pins on the flip-flop, and to 5 volts and ground, we're getting that same exact megohm reading. I was just looking electrically to see if one of these was just shorted to ground, and it doesn't appear that they are. So that doesn't, unfortunately, really help us. The problem really could be either one of these two chips. It could be the output of the flip-flop, or it could be the input of this that's keeping it at ground. One way we could actually test is cut the pin halfway up from the board. So you could probe the output of the flip-flop without actually removing it entirely from the board. That's just a good way to test, as long as you disconnect the connection between these two chips. If you're now suddenly seeing an output from the flip-flop, then that pretty much confirms it's this chip. It still could be a bad buffer driver that couldn't even drive the output of this, but that's unlikely in my opinion. You would still see some amount of signal, but we were seeing basically nothing, just barely any activity. Okay, I'm just gonna remove the entire chip. All right, I removed the chip, put it in a socket, and then I bent out the pin. So that pin, which goes to this chip, is no longer in play. So we can do two things. We can check the output of the pin here while this thing is running, and then we can also try to bring this pin up to 5 volts through a resistor and see if that's possible, and see if we get the attribute and that row of pixels or that column of pixels that we're expecting. And in case you're wondering, I did use this to inspect the board just to make sure I didn't short anything, because I seem to have a track record for doing that. Okay, here we go. What are we gonna get? Oh, we have white text. So that means that that chip, the input to the chip, is probably defaulting to pulling up to 5 volts. Now what's happening is that the red is stuck on all the time. Therefore, we're not getting things like green or cyan because that doesn't have a red component. Okay, so this is behaving exactly as I would have expected. Now in the graphics mode, we should be getting lines now of purple, and then where there were white boxes, it should actually be white. So let's see if that looks that case. If that's the case, no. That's still not quite working exactly like I would have thought. I would have assumed since it was pulled high, that we'd be seeing lines. But I guess it's the shift register that displays the pixels behaves differently, and it probably doesn't pull up to 5 volts internally. So I need to find another flip-flop and get that installed, and hopefully that fixes all the problems. Okay, I have an ACT374 installed in here. It should be fine, TTL compatible, and this was salvaged off another board. Occasionally I have these scrap boards and I take some chips off there to put into stock, and this was one of them. So here we go. Let's see if this thing is working still. Oh no! Okay, well, that's really interesting. Right, I'm quite confused. Let's scope the output to that pin. Okay, so we're on pin 14, that's the input, and that's the output. It's just nothing. And that's the output 7Q, and that the input. Is this chip not working correctly? That's the clock signal. That looks normal. And I have the graphics mode up here. Let's scope that pin, because that's how we were doing it before. Let's look at pin 6 now. Well, it's not pin 6, it was the unit 6. Yeah, okay, that is just grounded still. What I didn't do is I'm gonna put the other chip back in there with the lifted pin. And we're gonna take a look at the lifted pin, at the output there. All right, so the original one's back in with that pin lifted. The text is now looking better as we saw before. So back on the high-res graphics, same test setup. And here I am on the body of the chip on the lifted pin. So it's not in the socket at all, it's just floating. And this is an output and we're at ground. It kind of implies that even though we're seeing input signals here, when this is being clocked, it's never actually trying to output a signal. And I feel that we're on the right path, but I think I went one step too far. So the chip that I took out of the board here is fine. And this chip is actually the next phase after something else that's broken in front of it. So whatever is going into this unit here on pin 6, I need to trace this to something on the board, because I think that chip is where the fault is. It's not with this one at all. And I kind of wonder on the mux here, so this is the input to the mux. Again, it's just kind of floating here. I'm gonna try pulling this to 5 volts and let's see what that visually does to what we're looking at on screen, if anything. So this is the pin that originally goes to, so this is the one that's floating, and I have a resistor here. I'm gonna try pulling this to 5 volts and to ground, and let's see what it does visually on screen. Okay, so first I connected to ground, and there it is. So absolutely, that pin is responsible for the attribute color that we're having the problem on. When I pull it off, it goes away, and if I connect this resistor to 5 volts, no change whatsoever, which is kind of what we would expect, because it seems to be just sort of internally pulled up to 5 volts. Now, when we go to the graphics mode, on the other hand, I don't think doing anything with this ground or otherwise, so that's on ground and there's no effect, or 5 volts. Yeah, it doesn't really do anything, because this chip here, and I guess this flip-flop, is solely responsible for the attribute bit. So I think what happened here is that the chip I took out is one chip beyond where the problem lies. And I have a feeling that this chip is only handling attribute-related stuff, which is why it had no effect on the graphics. We're onto something here with this, but I need to find where this goes. I need to find where the input to this chip actually goes on the board. And hopefully that's the bad chip. Now, I have to admit that I definitely was lucky that we're kind of onto the right track here, but I took the wrong chip out. And I think I just kind of, I don't know, ignored what I thought I knew, that it was this chip here. Did I just erase the dot that was on this chip? I thought it was this one, but I think I erased the mark just now with the alcohol. I just tried to get the X off that chip, and it's either one of these. I think it's just gotta be. So we know that this is the output pin for the bit that's having an issue, and it goes into there. So we need to find where this pin, which is the input for this unit, is going, so that we can figure out which chip that goes to and then try to make heads or tails of what we're seeing there. Okay, so we know that's the output. That was the one that goes over here. That was having an issue. This is the input pin. This pin here makes its way to this flip-flop right here, this with a little white mark, which is an output. And the input to that unit is with the red mark on it, and it's found here on this DRAM chip on one of the data lines. So that could be the issue, but I don't necessarily think so. And the reason why is the other connection, so this red mark here goes to the RAM chip. It also goes over here to this chip, and this right here is an output. And the input of this chip goes to the ISA bus on one of the pins here. And that's obviously one of the ways that information is sent from the computer into the DRAM. But I think this part over here has to do with the ISA bus communication and is not what we need to focus on. I think what we're dealing with is something over here. So this chip here, I need to take a closer look at the input and the output here just to see if this output does what we think it should. It goes from here to the input of this chip, which we know is going to there. And I'm kind of assuming that the output of this chip, which goes there, must go somewhere else on this board. And I didn't immediately find it, but it's difficult when we don't have the schematics just to probe around, kind of look for it. I need to kind of look around, see if I can find the other place this goes. It's got to go to two places. It's kind of gotta. So one way to help find this stuff is to use these brush type probes, and we have that connected up there. So I'm on this pin here, which obviously goes there, and now I can just kind of go around the board like this and try to find, where it goes. And then once you get to the area, you can use a more exacting probe to find exactly which pin it goes to. Okay, it's something over here. So switching back to my regular probe here. Yeah, okay. That pin right there. Oh no, that's horrible. I'm not immediately jumping to conclusions that that's the problem over here, because we know the issue exists in the attribute area as well. So I kind of still suspect that it's this flip-flop here that's the problem. And I wouldn't be surprised if this, which I can't really make out what it says, something mux, CLA mux, that could be something to do with the graphics maybe. And if this is the problem right here, then this could be handling graphics. This could be handling the attribute data, like through that flip-flop here, right? I have to hope. All right, so the signal on the mux that we suspect might be having a problem, the output, is that, which looks to be exactly the same as the clock signal. It's basically identical. And that's making its way over here to this mux here, which the output is just ground, right? And we know that's causing the attribute problem based on the input here. Okay, now we have the text pattern up here. Let's look at what the signals look like now. Okay, so double checking, that's the output going to the attribute bit, the mux or whatever. It's stuck at ground, so that's why we're getting the blue text. And then that's the input that still looks like the clock signal that's coming from this other chip. And that is the output of this one here, the one I suspect might be bad or whatever. It looks like the clock signal, which is right there. And the input there to the gate, it looks like that. And this is what's coming from the DRAM itself. If I go on the pin on the DRAM, you see it's the same thing there. Now here's the thing, if I go to the flip-flop right next door, we are on pin 17, 7D, if you look at the pin out there. That's from the DRAM as well. And we look at the output of that flip-flop unit, and it looks like it should look. There's no clock signal in it. And we go back to 6D, that's from the DRAM, looks fine. The output though, it's got that clock signal on it. And that makes no sense. Now here's the truth table for the 374. That's what's on this board. And you'll notice the D, which is the input's either high or low, and the output's either high or low. There's no situation where the output would be high and the input low, or vice versa. The output always mirrors what the input is. It's just when the clock signal is low that the output can actually be Q0. Now what's Q0, you ask? I'm not sure. I don't know how these chips work exactly. So it says here, the 8 flip-flops are edge-triggered D-type flip-flops. On the positive transition of the clock, the Q outputs are set to the logic states that were set up at the D input. So it just copies what's on D to the output. And then the output just stays there. It doesn't really say what Q0 means, but I'm gonna have to infer what that means is it just keeps outputting whatever Q was last set to. So when the clock goes up, it copies the input to the output, right, from D to Q. And then when the clock goes down, if it just stays down, the output Q just stays at whatever value, whether high or low, that it was set to originally based on whatever D was. It should never toggle on and off based on the clock input. It should just stay at what it was originally at. Now, what has me worried here is that the PAL chip here, which we know this pin is also getting that weird clock signal, is this somehow an output that's forcing that clock signal onto that signal? I can't quite make out what kind of chip this is, but all I can think to do here is pull this out of the board and bend that pin out, since this is in a socket. And then we can kind of see if that has any kind of an effect on the overall system. So I'm just going to lift this pin out here, just like that, and put this back in the board. Now, if this chip is the problem, by the way, I'm kind of screwed. There's no way to recover from that. This is a custom chip. It's been programmed. There's no way for me to make another one. So let's hope the issue exists over here. If when we turn this on, we see the same behavior with that weird clock signal coming out of the output of this chip, then that pretty much confirms I think there's a problem with this chip. I have no idea if the system's going to run with that pin out of there, but we'll see what happens. Okay, here we go. Okay, no change. I'm curious if there's going to be any visible difference here. That all looks the same, so no change on the graphics side of things. Wow, it all looks exactly the same as well. So this is the input that's coming from the DRAM on 6, so that's 6D, and let's look at 6Q. Aha, it looks the same. So it's not coming from this chip over here, this weird clock signal. It's overlaid on the signal. This is definitely coming from this flip-flop itself. So it's got to be this chip that's bad. It's got to be. I think the issue is somehow the clock is like leaking through to the output on this flip-flop. So it's not just a dead output, but it's leaking through. And the overlaid clock somehow causes this chip, which handles the attributes, to always just not have the red. So I just put that pin back in over here, and I'm going to socket this chip now. And then we can try out this Fairchild part in here, see if that fixes it. Okay, the possibly bad chip has been removed, replaced with a socket and that Fairchild IC we were trying to use before. And for some suspense, let's not plug anything into the video output. Let's just scope those signals on here and see if that weird clock signal thing has gone away. And I guess what we can also do is take a look at the output of this IC here and see if we actually see stuff on there when we power this machine up. All right, let's power the machine on. It's posting. Okay, I think, let's see, what are we looking at here? That's the RAM input. Oh, yeah, that's it. That was the output right there. And we weren't seeing anything weird. Let's take a look at the output of this IC, and that is not stuck at ground anymore. It's up at 5 volts, which I think is exactly what we should be seeing. Because remember when it was pulled high, when we pulled the chip out, or we had the leg bent out, we were seeing the normal colors. So I have the video connected up. Let's switch the inputs, see if it looks good. Oh yeah, okay, that is great. Now, we still could be tricked because we were last time. What we need to do is bring up the actual color test pattern here. So we gotta go to video and we gotta do text. Oh yeah, it's working. That was it. It was that flip-flop. Let's get to the thing. There it is. All the colors are there. Okay, now question is the graphics mode fixed as well? I'm presuming it is, and that the output of this chip, which was messed up with that clock signal, is going somewhere else on the board that's also handling the graphics mode. And the way for us to know is run graphics. Yes, fixed, freaking fixed. It freaking works. It was this bad chip all the time, and I have to say, I've never seen that particular failure before, where it wasn't stuck at 0 or 5 volts, the output. It was leaking the clock signal, but kind of working, because we saw sometimes it would be low when the DRAM input was low, but when it was high, instead of just staying high, it was getting that clock signal on there, and that was causing, well, those particular symptoms that we saw. So what I need to do now is we'll turn this off, and I need to reinstall these RAM chips, which I removed, that bring this thing back up to the full 64K. And I must say, I'm extremely relieved that there's obviously or seemingly no problems with these PAL chips that are on here, since I have zero way to possibly replace those. And with the RAM in there, well, we just need to make sure this thing is still working properly with it all fully installed. But there's no way for me to even test those modes because I don't have any software. Yes, looks good. Awesome. RAM test, we're looking good. All the pages of text are working. 40 column looks good. 80 column looks good. This so far so good. Everything looks good there. Perfect. Everything is working. 320 by 240 looks good. These modes look perfect. 640 by 200, perfect as well. And then these look good. Yeah, freaking awesome. Freaking awesome. Now what I'm gonna do is I'm gonna use a little bit of acetone here. I just wanna remove the Sharpie marks that I have all over the board here. There's no reason to leave these on here. So we'll just clean them off a little bit. And there we have it. One fully repaired STB Super Res 400. And what was actually wrong is this LS374 in this position here was leaking the clock signal for the latches, that is, onto that particular output that was causing that weird symptom. And when I think about lessons learned from this exercise, I did accidentally remove and socket an IC that I shouldn't have. And really where I got caught up is that I had identified which were the candidate chips that were potentially the problem. It was 2 over here and 2 over here. And I had identified the bad one. But when I went through and looked at all the inputs and outputs, I didn't really pay attention to the fact that the input and the output needed to match. And I guess I just breezed by those 2 pins. And I think I just missed that. And I should have used my brain a little bit more to think about the way these flip-flops work, and that the output should have never had all that clock signal on it. And that would have clued me in immediately that that was the bad chip that was potentially causing these issues. Right, I'm editing the video and I see exactly what happened here. The test pattern I was displaying when I was teching the inputs and outputs of the bad chip, we had the 640 by 200 grid pattern up. And that was obviously the wrong pattern to be testing with, because here I am testing the bad pin, and the only time that clock signal leaks through onto this is when the signal is up at 5 volts. But most of the time when we're looking at the grid pattern, it's down at ground, which is why I didn't notice the pulsing that was happening when it was up at 5 volts. And I think if I had had a text mode enabled when I was testing this chip, we would have seen much more of the bad signal, which I think I might have caught in that initial phase of testing. Now I did get there in the end, but I feel that that was kind of luck, and that just happened to be because that weird clock signal leaking onto here was causing the output of this one to always look like it was down at ground, which I just assumed was a fault, when the reality was it wasn't. It was just that clock signal leaking in and causing that to always look like it was there at ground. With all that said, I'm going to still claim job well done, because the evidence I collected in analyzing the faults on this board did bring me generally to the exact area where the fault was. I knew it was either going to be with the 374s over here or the ones over here. And what I needed to do a little bit better was just analyze the signals going in and out of the chips that I thought were faulty, and I would have more quickly been able to figure out exactly which one was the problem. If I had the schematics for this board, it would have been so much easier. And that's one of the issues when you don't have them, is you have to kind of reverse engineer and spend a lot of time tracing out and trying to figure out where the traces go. And on boards like this, it's really hard because it's very tightly packed in there. And the traces make their way all over the board, and they go through vias, and they're underneath all these chips. So there's no real way to do it visually. You actually have to use that brush I was using to try to figure out where the traces go. And like I said earlier, I'm pretty sure that the bad signal, besides going to this PAL chip and this other 374, must have gone somewhere else on the board that I didn't find. To be honest, I didn't really look at these other PALs over here, and it probably went into one of these that forms the graphics engine of this board, like creates that bitmap graphics. Anyhow, the board is fixed, and that's what's important, because I can go work on another video where this thing is going to be a supporting role and not the main attraction, and I just needed this thing fully operational, and now it is. So once again, if you know about any software that might work on this so I can run it in 16 color mode, or maybe some of those other high-res modes, let me know. Or if you happen to know where the drivers or manual is for this from STB, that would be even more amazing, because then I could run like Lotus 123. Well, I don't know what I'd want to do with that, but maybe I could run something that could generate some high resolution graphics or something and look really cool, and that would be awesome for this kind of unknown card. So with all that said, if you like this video and this troubleshooting exercise, I'd appreciate a thumbs up, but if you didn't, you know what to do. Thanks to my supporters. Their names are up beside the screen. Subscribe if you haven't already, I really appreciate that, and you know, all the usual YouTube junk. And I guess that's gonna be that, so stay healthy, stay safe, and I will see you next time. Bye-bye. Wow, it's absolutely pouring with rain outside.